Let us say maximum power transfer theorem. The maximum power transfer theorem states that the maximum power transferred in the circuit when the load resistance is equal to the internal resistance of the circuit. Now let us say statement of maximum power transfer theorem. It states that the maximum power transfer from a source can be transferred when load resistance RL is made equal to the internal resistance. So from statement, the maximum power is transferred to the circuit in the condition of the load resistance is equal to the internal resistance. Hence RL is equals to internal resistance. Ra, let Ra. Here, if we draw the circuit for maximum power transfer theorem, then the circuit look like this. This is RL in between these points, and this is internal resistance or equivalent resistance, which is calculated by removing RL and which is connected to voltage source. So up to here, this is a circuit we want to simplify for the problems. Let it be RIR, here simply R. So I am taking R here. Let current through this RL is IL. If we write IL equivalent, then IL is equals to, from Ohm's law, V by R. Here R is R plus capital RL. Now let us take power transferring through RL is power transfer to RL, which is given as PL is equals to I square into R. Here IL square into RL. Here we derived IL equals to V by RL plus capital RL into whole square into RL, which is PL. To get maximum power transfer through the circuit, I am deriving this equation 1 with respect to RL. Now to get maximum power transfer, differentiating equation 1 with respect to RL. If we do this, then the equation of 1 is transferred to this, like to RL d by dRL of V by R plus capital RL of whole square into RL. For maximum, this dPL by dRL is equals to 0. Now dPL by dRL is equals to 0 for maximum. Taking V as common and writing up, I am writing V in outside of this equation. So this is look like this, V square into dRL by of 1 by R plus capital RL of, here this square is transferred to V and R plus RL also. So I am taking here only. I am writing this RL2 inside. So the equation look like this. Now this is in form of U by V. Derivation of U by V. Derivation of U by V is formulated as V U dash minus U V dash by V square. Hence we are using this formula to solve this equation. If we write this equation in this form, then the equation is look like this, V square of, here Here taking V, which is R plus capital RL of whole square, and U dash, which is RL dash. L we are differentiating with respect to RL. So RL DRL by DRL is equals to 1 minus, again here writing U, here U is nothing but RL into V dash. V is similar to R plus RL, so here this is power, so power comes forward 2 into R plus capital RL. Differentiate this, so we are left over with this D smaller by D capital RL, which is 0, and D capital RL by DRL, which is 1 by V square, R plus capital RL of whole square into whole square. Now if we simplify this equation, we are going to get this R plus RL whole square, writing 1, which is not effect, so 2RL into R plus RL, 0 plus 1, which is 1, writing 1, which is not effect, so by R plus capital RL power 4. Now this all are equal to 0, so equal to 0. Now take and go this V square to other side, this V square is going to cancel, and also take and go this R plus RL power 4 to other side, this is going to cancel, R plus RL whole square minus 2RL of R plus RL, which is equals to 0. Now take and go this term to other side, then the equation look like this, which is equals to 2RL of R plus RL. Here square and this term is going to cancel, again we are left over with R plus RL into 2RL. R is equals to 2RL minus RL, then R is equals to capital RL. Therefore we got internal resistance is equals to load resistance. When this condition is applied for maximum power transfer in the circuit. Now substitute RL is equals to smaller, then each one is changed to PL is equals to V by R plus R of whole square into here we are, this is as V square. Now the maximum power transfer in the circuit is V square by 4R. This is the important formula in solving the maximum power transfer theorem problems.